So algebra. So we have 2 more classes today and Monday, and I'll be going over review problems for the final exam. I sent out 1 sheet of review problems and covering number theory and group theory, and I'll have a second shorter sheet covering some problems in ring theory that I'll send out before the weekend. Any questions before we start? So let me just start going through some problems on the review sheet. And if you have questions you'd like me to do, you can just interrupt and ask me to do them, but I'll start with number 1. So if you want to find the greatest common divisor of 2 numbers, Euclid, 2,500 years ago, knew how to do that. So suppose we take the number A to be 2,241 and B to be 1162. And the Euclidean algorithm says just keep dividing one number by the next until something divides evenly. So for example, if you divide 2241 by 1162, that goes in 1 time, and the remainder is what? 2241, 1162, subtract. $79. And then you take 1162 and divide it by 79. And how many times does that go in? Well, do a little bit of arithmetic, I guess. So it's roughly 80 going into something like 1200, or 8 into 120. And I think it goes in 14 times. And if you take 79 and multiply it by 14, you get a remainder of 56. Oops, plus. So I hope someone's checking my arithmetic, because it's hard to always do this right. Let's see. 38 and 41 is 79. 1162 divided by 79 is 14 and a remainder of 56. I hope that's right. 79 divided by 56, that goes 1 time and leaves a remainder of 23. 56 divided by 23, that goes 2 times and leaves a remainder of 10. 23 divided by 10 goes 2 times and leaves a remainder of 3. 10 divided by 3 goes 3 times and leaves a remainder of 1. And 3 divided by 1 goes 3 times and leaves a remainder of 0. So the last positive remainder is 1. So the greatest common divisor, the GCD of 1162 and 2241, is equal to 1. And if you want to write 1 as a linear combination with integer coefficients of 2241 and 1162, you just work the Euclidean algorithm backwards. So you say 1 is 10 minus 3 times 3, which is 10 minus 3, but 3 is 23 minus 10 times 2. So what is that? That's 10 plus 6 times 10. That's 7 times 10 minus 3 times 23. But 10 is 56 minus 23 times 2. So that's 7 times 56 minus 23 times 2 minus 3 times 23. That's 7 times 56. This is minus 14 times 23 minus 3 times 23. It's minus 7 times 23. The 23 is 79 minus 56. So I have 7 times 56 plus 17 times 56, that's 24 times 56, minus 17 times 79. And 79, oops, sorry, that's this. 56 is 162 minus 14 times 79. So 56 is 1162 minus 14 times 79 minus 17 times 79. Actually, didn't expect such big numbers. 24 times 1162 minus, I have 24 times 14, which is 336, plus 17, 353, minus 353 times 79. And then finally, 79 is 2241 minus 1162. So this is 24 times 1162 minus 353 times 2241 minus 1162. Hard for me to believe that this is all correct, but we'll check in a second. So I get 1 is equal to 353 plus 24. That's 377 times 1162 minus 353, 224, 2241. And I can tell just by looking that there's some mistake that can't possibly be right. The numbers just don't add up properly.
Professor, and the first line, I think is not 79, it's 1079. I just figured it out. And the first.
79. So as I go from step to step, where did I make a mistake?
At the beginning of the problem, when you say 2041 equals 1162 times 1 plus.
Yes. Why did I do that? So I'm going to start on a new piece of paper and hope I can do better. So 2241 is 1162 times 1, and the remainder is, I forgot to look at the thousands, didn't I?
1079.
10,079. And then 1162 is 1079 times 1 plus, let's see, 21 and 62 is 83, I think. Is that right? And so I take this, and I get this remainder. And this divided by this goes in one time and leaves a remainder of 83. If I take 1079 and divide it by 83, looks like I get 13. So So the GCD of 1162 and 2241 is the last positive remainder, 83. And this says, if this is correct, 83 is 1162 minus 1079. But 1079 is 2241 minus 1162. So this is 2 times 1162 minus 2241. And that looks like it's okay. So the answer is the GCD of these two numbers is 1183. And I think if you check, well, this is really one check, but 2241 is divisible by 83 is 83 times 27. And 1162 is 83 times 14. So if you let x equal 2 and y equal minus 1, 83 is 1162x plus 2241y. These are the values for x and y. Okay. Ooh, good. Thank you for finding where I made the mistake. Let's look at number 2. R, S, and T are positive integers. We want to show that if R divides ST and R and S are relatively prime, then R divides T. So if R and S have greatest common divisor 1, then you can say there exist integers x and y such that Rx plus Sy equals 1. If you multiply this equation by t, you get Rtx plus Sty equals t. But we're also told R divides T. So T is R times D for some number D. So I can substitute that in here. Oops, let's see. Sorry, we're told that R divides ST. R divides ST, so ST is R times D for some divisor D. And I can put that in here, so I get RTX, ST is RD plus RD, Y equals T. And if I factor out the R, it says R times TX plus DY equals T, which means exactly R divides T. T is R times some integer. That's the proof. Let's look at problem 3. If A1 is congruent to A2 mod M, that means A1 minus A2 is M times some integer X. M divides the difference. And if B1 is congruent to B2 mod M, that means that B1 minus B2 is a multiple of M times Y for some integer Y. So I can write this as A1 is A2 plus MX, B1 is B2 plus MY. And if I subtract these equations, I get A1 minus B1 equals A2 plus MX minus B2 plus MX plus MY. That's A2 minus B2 plus M times X minus Y, which means exactly that A1 minus B1 is congruent to A2 minus B2 mod M, because the difference is a multiple of M. Okay. Any questions about that? So in problem 4, you want to solve some congruences. X congruent to 13 mod 16. X congruent to 5 mod 56. So if X is congruent to 13 mod 16, that means X is equal to 13 plus 16Y for some integer Y. So if I substitute that for X here, that says 13 plus 16Y should be congruent to 5 mod 56. Or 16Y is congruent to 5 minus 13 minus 8 mod 56. This means you want to find the Z such that 16Y minus 8 plus 8 is 56Z. If I divide by 8, I would get 2Y plus 1 equals 7Z. Or 2Y congruent to minus 1 mod 7. Exactly what I would have gotten if I divided each of these numbers by 7. And this has an obvious solution. Y congruent to 3 mod 7, because 6 plus 1 is 7. So I can let Y equal 3 plus 7Z, and then X, which is 13 plus 16Y, is 13 plus 16 times 3 plus 7Z. See, we're making a lot of mistakes today, so let me just double check everything like that. X is congruent to 13 mod 16. The next is 13 plus 16Y. So 13 plus 16Y has to be congruent to 5 mod 56, where 16Y is congruent to minus 8 mod 56, where 2Y is congruent to minus 1 mod 7. So you can take Y to be 3 plus 7Z. So Y is 3 plus 7Z. So X, which is 13 plus 16Y, is 3 plus 63 plus 7Z. So this is 13 plus 48, that's 61, plus 16 times 7. 16 times 7 is 8 times 56 is 2 times 56.
112.
112. So the answer is any X congruent to 61 modulo 112. And let's check. 61 minus 13 is 11 take away 3 is 8. It's 48, which is congruent to 0, mod 16. And 61 minus 5 is 56, which is certainly congruent to 0, mod 56. So this is the solution. In fact, the Chinese remainder theorem would say that this pair of congruences has a unique solution modulo the least common multiple of 16 and 56. And that least common multiple is 112. So this first pair of congruences has a solution. Any questions about that? Let's look at part B. We have another pair of congruences. 3x congruent to 2 mod 7 and 5x congruent to minus 1 mod 10. Now 3x congruent to 2 mod 7, if we solve that congruence, that's the same. So the 3 and 7 are relatively prime. This will have a unique solution. The unique solution is x congruent to 3 mod 7. Because if x is 3, you get 9. 9 minus 2 is 7. And 5x congruent to minus 1 mod 10, well, that has no solution. If there were a solution, 5x minus would be equal to minus 1 plus 10 times something, but 5 divides 5, 5 divides 10, doesn't divide minus 1. So this congruence has no solution. So the pair of congruences certainly has no solution. Remember, there's the basic theorem for linear congruences. It says that AX congruent to B mod M is solvable, has a solution, if and only if B is congruent to 0 modulo the greatest common divisor of A and M. So in this case, 5x congruent to 1 mod 10, the greatest common, so A is equal to 5, M is equal to 10. The greatest common divisor of A and M is the greatest common divisor of 5 and 10, which is 5. And minus 1 is not congruent to 0, mod 5. So if one of the two congruences has no solution, then certainly any system it's part of cannot have a solution. Okay. Questions about that? Problem 5, we're looking at permutations in the symmetric group S10. So sigma is the permutation 8, 5, 10, 4, 6, 7, 3, 9, 1, 2. And to write this as a product of disjoint cycles, you can just take an element and start to follow it around. 1 goes to 8, 8 goes to 9, 9 gets sent back to 1. So there's a 3 cycle. Let's say I look at the next number I haven't used, 2. 2 goes to 5, 5 goes to 6, 6 goes to 7, 7 goes to 3, 3 goes to 10, 10 goes back to 2. And what number hasn't been used yet? Only the number 4. And 4 goes to 4. So I don't even, I can write it or not write it, but this is sigma as a product of two disjoint cycles. And how do we write this as a product of transpositions? There are many, there are infinitely many ways to do it, in fact. But 189 is 1819. If you look at this product of two transpositions, this sends 1889. It's a little bit better. 1889. So this sends 1 to 1 to 8, 8 to 9 to 9, 9 to 8 to 1. And 2, 5, 6, 7, 3, 10. You can always, there are lots of ways to do this. You can write this as 2, 5, 5, 6, 6, 7, 7, 3, 3, 10. Just break this up into successive pairs of transpositions. And we prove that, in fact, this always works. So sigma is the product of these two times these 5 transpositions. There's 7 transpositions in this group. What is sigma squared? So we iterate, we apply sigma twice. 1 goes to 8 and 8 goes to 9. 2 goes to 5 and 5 goes to 6. 3 goes to 10 and 10 goes to 2. 4 goes to 4 goes to 4. 5 goes to 6, 6 goes to 7. 6 goes to 7, 7 goes to 3. 7 goes to 3, 3 goes to 10. 8 goes to 9, 9 goes to 1. 9 goes to 1, 1 goes to 8. 10 goes to 2, 2 goes to 5. So sigma squared is this permutation, and it's a product of disjoint cycles. 1 goes to 9, goes to 8, goes back to 1. 2 goes to 6, goes to 3, goes back to 2. 4 goes to 4. 5 goes to 7. 7 goes to 10. 10 goes back to 5. So sigma squared is a product of three cycles. Yeah, product of three cycles. And what about sigma inverse? So you look at sigma, 9 goes to 1, so the inverse sends 1 back to 9. 10 goes to 2, so the inverse sends 2 back to 10. 7 goes to 3, so the inverse sends 3 back to 7. 4 goes to 4, so the inverse sends 4 to 4. 2 goes to 5, so the inverse sends 5 to 2. 5 goes to 6, so the inverse sends 6 to 5. 6 goes to 7, so the inverse sends 7 to 6. 1 goes to 8, the inverse sends 8 to 1. 8 goes to 9, so the inverse sends 9 to 8. 3 went to 10, so the inverse sends 10 to 3. So this is sigma inverse, and is a product of disjoint cycles. 1 goes to 9, goes to 8, goes back to 1. 2 goes to 10, goes to 3, goes to 7, goes to 6, goes to 5, goes back to 2, and 4 just goes to 4. Okay. Let's look at problem 6. We have to do a matrix calculation. So S is the matrix 0, minus 1, 1, 0. And T is the matrix 1, 1, 0, 1. S squared, you multiply the matrices, you get 0. Sorry, you get 0 times 0 plus minus 1 times 1. You get minus 1, 0, 0, minus 1. So S squared is this matrix, which is minus, if you like, 1, 0, 0, 1, or minus the identity, but that's where I leave it. If T is 1, 1, 0, 1, we want to find the inverse. So find a matrix T inverse. That means that T times T inverse and T inverse T is the identity. The identity is 1, 0, 0, 1. And let's say there are easier ways to do this, but say you didn't know how to do it. So suppose we want to let T inverse be some matrix A, B, C, D, and we want 1, 1, 0, 1 times A, B, C, D to be equal to 1, 0, 0, 1. So we want to solve this matrix equation. When you multiply these two matrices together, you get A plus C, B plus D, C, D equal to 1, 0, 0, 1. But this means C equals 0, D equals 1, A plus C equals 1, but C is 0, so A is 1. B plus D equals 0, D is 1, so B has to be minus 1. So this matrix A, B, C, D is A is 1, B is minus 1, C is 0, D is 1. And you can check by multiplication that the product of these two matrices is the identity. If you multiply S by T, what do you get? You get 0, 1, minus 1, 1. That's ST. What would be ST squared? This is ST. You multiply it by itself. You get 0, 1, minus 1, 0. What is ST cubed? So ST cubed is ST times ST squared. ST is 0, minus 1, 1, 1. ST squared is 0, minus 1, 1, 0. So when I multiply this, I get minus 1, 0, 1, minus 1. So if I was lucky and did my arithmetic correctly, this is ST cubed. Any questions about that? All right. Problem 6B. t is 1, 1, 0, 1. Prove t to the n is 1n, 0, 1 for all integers n greater than or equal to 0. Well, of course, t to the 0 always means the identity, which is 1, 0, 0, 1. So it's exactly this with n equals 0 here. And t to the first power is t, which is 1, 1, 0, 1. T squared, 1, 1, 0, 1, 1, 1, 0, 1. That's equal to 1, 0, 2, 1. Exactly what this says. When n is 2, we have a 2 here. So we'll prove this now by induction. Suppose for some integer n, t to the n is 1n, 0, 1. So t to the n plus 1 is t to the n times t. That's 1n, 0, 1, 1, 1, 0, 1. And when you add and when you multiply, just doing matrix multiplication, this is what you get. N plus 1 here. So if this statement is true for n, it's true for some n, it's true for n plus 1. Therefore, it's true for all n. And part C is to prove that t to the m times t to the n is t to the m plus n. But the simplest way to do this is to use part B. So we know t to the m is 1m, 0, 1, and t to the n is 1n, 0, 1. So t to the m times t to the n, 1m, 0, 1, 1n, 0, 1. When you do your matrix multiplication, you get 1, m plus n, 0, 1. And this is exactly t to the n plus n. So that's the proof. Questions so far? Problem 7 is just to check that the rule for multiplying determinants is correct in the case of 2 by 2 matrices. So we have X is the matrix A, B, C, D, and Y is the matrix E, F, G, H. And if we multiply them, A, B, C, D, E, F, G, H, what do we get? We get A, E plus BG, AF plus BH, CE plus DG, CF plus DH. So the determinant of the matrix XY, it's this times this, AE plus BG times CF plus DH minus this times this, which is AF plus BH, CE plus DG. So now it's just a calculation. I get ACEF plus ADEH plus BCFG plus BDGH minus ACEF minus ADFG minus BCEH minus BDGH. And hopefully there's some cancellation. So here I have plus b dgh, and here minus b dgh. So these two cancel. Here I have ACEF, and here I have minus ACEF. So these two also cancel. So I'm left with four terms, ADEH minus ADFG plus BCFG minus BCEH. So I can factor AD from the first two terms, AD times EH minus FG. I can factor with BC from this. Let me write this as minus BC EH minus FG. And now I can factor out EH minus FG. I get AD minus BC EF minus EH minus FG. And this is exactly the determinant of X, and this is exactly the determinant of Y. So that's one of my favorite calculations. Shows directly the multiplicativity of the determinant for 2x2 matrices. Questions about that? Let's look at problem number 8. We have a group G, elements X, Y, and G, and the commutator of X and Y is defined to be X inverse, Y inverse, X, Y. And then it's easy to see that the commutator is equal to the identity. That means X inverse, Y inverse, XY equals the identity. If I multiply both sides by X, I get X inverse, Y inverse, XY equals X. But X inverse is the identity. So that just says Y inverse XY equals X. If I multiply both sides again on the left by Y, I get Y inverse XY equals YX. But Y inverse is the identity. So that just says XY equals YX. So we've seen this already several times before. The commutator of two elements in a group is the identity if and only if X and Y commute. So XY equals E if and only if X and Y commute. And that's the definition of commuting. Two elements commute. It doesn't matter what order you multiply them in, XY or YX, you get the same element. Right. Problem 9 is just a little set theoretic calculation. We have sets A, B, C, oops, I should have said A, B, C, and D. So if I take B intersect C intersect D, and I take the union of A with that, I want to show there's a kind of distributive law. This is A union B intersect A union C intersect A union D. So we want to prove this identity. So the way you do, one way to show two sets are equal is to show that each is contained in the other. So if X is in A union B intersect C intersect D, then we have two possibilities. either one or both holds, then either X is in A or X is in B intersect C intersect D. So let's look at both cases separately. If X is in A, then X is certainly in A union B, X is in A union C, X is in A union D. So X is in, if it's in all three of these sets, it's in their intersection. That's what I wanted to show. If X is in this, then X is in the intersection of these three sets. So in the first case, if X is in A, then that's true. And in the second case, X is in B intersect C intersect D. So that means that X is in all three of those sets. So if X is in B, it's in A union B. And if X is in C, it's in A union C. And if X is in D, it's in A union D. So X again belongs to all three of these sets. So X is in the intersection. So that proved half of the theorem. It proves the set on the left-hand side is contained in the set on the right-hand side. Now let's prove the converse. So suppose Y is in A union B, intersect A union C, intersect A union D. Again, there are two cases. If Y is in A, then Y is certainly in A together with something bigger, B intersect C intersect D. And if Y is not in A, but it's in A union B, then Y is in B. And if it's not in A, but A union C, then it's in C. And if it's in A union D, but not in A, then it's in D. So Y is in B intersect C intersect D. So it's certainly in A union B intersect C intersect D. So that is the complete proof of that result. Right. Let's look at number 10. So I is a non-empty set of integers closed under subtraction. So that means that if A and B are in the set I, then A minus B is in I. And we want to prove that I is the set of all multiples of some non-negative integer D. D times Z, all multiples of D. So first of all, I is not empty, means there exists an A in I, and I is closed under subtraction, so A minus A is an I, which is 0, so 0 is an I, and that means that 0 minus A, which is minus A, is an I. So the fact that A is a non-empty tells us that it contains 0. And if it contains A, then it contains all negative A's. So of course, there are two cases. Case 1 is I just consists of 0, which is all multiples of 0, because 0 times anything is 0. and we're done. We win. So if I only contains 0, I is the set of all multiples of 0. And of course, the case 2 is the interesting case where I is not just 0. So there exists some element A and Z, A different from 0, and minus A therefore is in Z. So A or minus A, one of those two has to be positive. So I contains some positive integers. And let D be the smallest positive integer contained in I. The smallest positive integer in I claim that I will consist of all multiples of Z. And the proof is just long division. Suppose we take an element A in I. By the division algorithm, you can write A is dq plus R, where the remainder is between 0 and d minus 1. So we know A is in I. We know D is in I. It was the smallest positive integer in I. All multiples of D are in I. So that means that an I is closed under subtraction also. A minus dq is in I. And this is equal to R. But R is between 0 and d minus 1. D is the smallest positive integer in the set I. So if I is non-negative and strictly less than D, that means less than or equal to d minus 1, then R equals 0. Which means A is dq, which is a multiple of D. So every element of the ideal is a multiple of D. Any questions about that? The 11 and 12 are problems of the sort I already did. So let me skip to 13 for the moment. I can always come back to them later, but it's more useful to cover new material. So problem 13, we have two permutations, a cycle 1, 3, 4, and a transposition 2, 5. So if I compute sigma tau, that's 1, 3, 4, 2, 5. Let's see, so this is a permutation, let's say, that just involves the first 5 integers. This sends 1 to 1, 1 to 3, so 1 goes to 3. This sends 2 to 5, and 5 goes to 5. 3 to 3 goes to 4. 4 goes to 1. 5 goes to 2. That's sigma tau. And what is tau sigma? So 1 goes to 3. 3 goes to 4. 4 goes to let me do it in the same way. 1, 2, 3, 4, 5. 1 goes to 1 goes to 3. 2 goes to 5 goes to 5. 3 goes to 3 goes to 4. 4 goes to 4 goes
You're
to
doing the same, Professor.
Sorry?
you're doing the same. It's 2, 5 first and then 1, 3, 4.
Oh, sorry, thank you. Okay, tau sigma. So tau is 2, 5, and sigma is 1, 3, 4. So 1 goes to 3, goes to 3. 2 goes to 2, goes to 5. 3 goes to 4, goes to 4. 4 goes to 1, goes to 1. 5 goes to 5, goes to 2. And if you compare, these are exactly the same permutations. So tau sigma equals sigma tau. And sigma and tau, so sigma and tau commute. That's what we just showed. Sigma tau equals tau sigma. Sigma and tau are also disjoint. That means the elements moved by sigma are different from elements moved by tau. So 2 and 5 only involve the numbers 2 and 5. 1, 3, and 4 only involve the numbers 1, 3, and 4. This set of numbers is different from this set of numbers. So these are called disjoint permutations. And the fact is that disjoint cycles commute. So if you have a cycle A1, A2 up to A sub K, and B1 up to B sub L, so AI is different from BJ for all I and J. That is, none of these numbers equals none of any of these numbers. So if you're looking to see how this acts on an element, so here's this permutation times this. Let me write the permutations in the opposite order. If you apply this to an element X, if X is one of the B's, it moves it to a different B, and this doesn't change it at all. So it's just wherever it's moved by the B. Here, if X is a B, it's not moved by, it's not one of these. This doesn't move it at all, but this moves it. And the actions are exactly the same. Like if BI goes to BI plus 1 here, it goes the same thing here and so forth. Disjoint cycles key. Let's look at problem number 14.
Can we see the last page, please?
This page?
Yes.
All this says is, it's really in words, it's not written down. The A's and the B's are different. So if you apply this to an element X, if X is not an A or a B, it passes right through. X goes to X. If it's a B, if it's say B1, this sends it to B2, and this doesn't affect the B's at all. So B2 stays at B2. If X is B1, this leaves it at B1, and this sends it to B2. And you check all the possible cases, and you see that these two permutations, products of disjoint cycles, act on every integer from 1 to n in exactly the same way.
Thank you.
So we have R is the real numbers. C It's the complex number. C star is the non-zero complex numbers. And we have a function from f, a function f from R to C, defined by f of the real number t is cosine 2 pi t plus I sine 2 pi t. So we want to show this is a homomorphism of the additive group of real numbers. So if you take f of s plus t, that's equal to cosine 2 pi of s plus t plus I times the sine 2 pi times s plus t. But we have rules for the sine and cosine of sums of angles. This is equal to cosine 2 pi s cosine 2 pi t minus sine 2 pi s sine of 2 pi t plus I times sine 2 pi of s plus t is equal to the sine of 2 pi s cosine 2 pi t minus sine of 2 pi s minus cosine of 2 pi s sine of 2 pi t. So let's look at this a little bit more closely. We'll take this term and this term. That's equal to cosine 2 plus s plus I sine of 2 pi s all times cosine of 2 pi t. And then I have minus, and here I have sine of 2 pi s times sine of 2 pi t minus I cosine 2 pi s. That's I cosine 2 plus s. Just double check if I do all this again. Oh, sine of 2 pi t, sorry, sine of 2 pi s plus t is sine 2 pi s cosine 2 pi t plus cosine of 2 plus s sine of 2 pi t. So what I had for this term is I have a sine of 2 pi t minus I. And I have minus sine 2 pi s sine 2 pi t, 2 pi t, plus cosine 2 pi s I, and minus sine 2 pi s. Both of those times sine 2 pi t. Minus 1 is the same as I squared. So I can write this as cosine of 2 pi s plus I sine of 2 pi s times cosine of 2 pi t. And this I can write as I squared, and then I can factor out an I, plus I times cosine 2 pi s plus I sine of 2 pi s times the sine 2 pi t. And then I can factor out these two terms. I get cosine of 2 pi s plus I sine of 2 pi s times cosine of 2 pi t plus I sine of 2 pi t. And this is exactly f of s, and this is exactly f of t. So using the addition formulae for the sine and the cosine functions, I prove that f satisfies this kind of functional equation. So f is a homomorphism of groups. F is from the additive group of real numbers to the multiplicative group of non-zero complex numbers. So this is a homomorphism. And what's the kernel? Kernel is everything that gets sent to the identity. The multiplicative identity is 1. So the kernel of f, it's all t and r, such that f of t, which is cosine 2 pi t plus I sine of 2 pi t, is equal to 1. Which means, when is this equal to 1? Sine of 2 pi t is no imaginary part. So you have to have sine of 2 pi t equals 0, and cosine 2 pi t equals 1. Cosine 2 pi t equals 1 precisely when t is an integer. And when t is an integer, sine of 2 pi t is 0. So this is all integers. So the kernel of this homomorphism is the group of positive and negative integers. And the image of f is the unit circle in the plane. If you take any point on the unit circle, this angle is t, this is cosine 2 pi t plus I sine 2 pi t. So the image is the unit circle. Okay. Any questions about that? All right, that was 14. Let's look at number 15. So we let H be the set of all ordered pairs x comma x for all real numbers x. So this is contained in R2. R2 is just the plane, and the points where the y equals the x coordinate, that's just the line y equals x. So this is my H. Zero, 3 plus H, it's just the set of all elements of the form 0, 3 plus XX, which is everything in the form x plus 3. It's just this line. Zero, 3 plus h. Just take any point on the line h and move it up 3 units. You're adding 0, 3 to. Point 0.25 is there, and 2,5 plus h. Oops, sorry. 2,5 is actually over here. That would have been 5,2. So 2,5 plus h would be everything in the form 2 plus x, 5 plus x, or x, 3 plus x, plus 3, x in r. That's exactly this. So the coset 0, 3 plus h equals the coset 2, 5 plus h. And what are the left cosets of h? So it's everything you can add to h, though you can say it's the set of all vectors of the form ab plus h, which is all vectors of the form a plus x, b plus x.
Sorry, do you mind sliding the paper up a little? Thank you.
So ab plus h, it's just the translate of this subgroup h, that's just this line, by a vector ab, that's a plus x, b plus x, for all x in R. Or you could just as write this as well as a b plus x. Oops, sorry, not a b plus x. It's the set of all a plus x, b plus x for all x in R. Or it's also the same as a set of all elements of the form x, b minus a plus x. That's in R. All right, that was problem 14. Sorry, that was problem 15. Okay. After 15 comes 16. So problem 16, we're looking at the cyclic group of order 20. Famous of 20. This is a squared, all the powers of a up to a to the 19th, plus a to the 20th equals the identity. The subgroup generated by a to the 10th consists of just e and a to the 10th. Because if you were to take a to the 10th and square it, you would get a to the 20th, which is e. So this is just a 2-element subgroup. the subgroup generated by a to the 5th, you have a to the 5th, square it, you get a to the 10th, cube it, you get a to the 13th, fourth power, you get a to the 5, 10, 15. You get a to the 20. What's the subgroup generated by a to the 15th? So you have a to the 15th, a to the 15th squared, which is a to the 30th. The 30 is 20 plus 10, and 8, let me just write it, a to the 20 plus 10. That's a to the 20th, a to the 10th. But a to the 20th is the identity. So the subgroup generated by a to the 15th so you have a to the 15th, which is the same as a to the 10th. You have a to the 15 cubed, which is a to the 45, which is a to the 20 times a to the 5, which is a to the 10th squared times a to the 5th. A to the 10th is the identity. You get a to the 5th. And finally, if I were to calculate a to the 20th, or a to the 15th to the 4th power, that's a to the 60th. That's a to the 20 times 3, a to the 20 cubed, or e cubed, or equals e. So the element a to the 15 has order 4, and the subgroup generated by a to the 15 consists of the identity, a to the 5th, a to the 10th, a to the 15th.
Sorry, Professor, for a to the 15th, and then wouldn't a to the 15th be the identity?
This is a group of order 20.
Oh, okay. Okay.
If you want to look at the subgroup generated by a to the 8th, this is the powers of a to the 8th. A to the 8th, a to the 16th, a to the 24th, a to the 32nd, a to the 40th. Now, a to the 24th is the same as a to the 4th. A to the 32 is the same as a to the 12th. A to the 40th is a to the 20 squared. That's e squared, that's e. And then as you keep multiplying by powers of a to the 8th, you just cycle through these same elements again. So the subgroup generated by a to the 8th, you have e, a to the 8th, a to the 16th, a to the 4th, a to the 12th. It doesn't matter what order you write these in. E, a to the 4th, a to the 8th, a to the 12th, a to the 16th. This is a group of order 5. Problem number 17, we're looking at the same group, gamma 20, generated by an element A that satisfies a to the 20th equals to the identity. That's the only relation. So define the function f from gamma 10 to from gamma 20 to gamma 20. We define this function by f of x is x to the 10th power. And this is a homomorphism. F of xy is xy to the 10th. So that's x to the 10th, y to the 10th, because x and y are powers of a generator. Cyclic group is a given. So this is f of x times f of y. The kernel of f, it's all x to the k, such that f of x is the identity. K is between 0 and 19. Those are the 20 distinct elements of the group. The kernel of f is all x. Let me just write it more carefully. So this is the definition of the kernel. It's all x in the group. In this case, the group is gamma 20, such that f of x is the identity. That means this is all powers a to the k, where f of a to the k is the identity. What is f of a to the k? Raises to the 10th power. That's a to the 10k equals the identity. What powers of a equal to the identity? So this is all a to the k, where 10k is divisible by 20, right? A to the exponent 10k, that's the identity precisely when this is a multiple of 20. So 10k is divisible by 20, or k is divisible by 2, which means all a to the k an even integer. An even integer between 0 and 18. And there are 10 of them. So the kernel of f is the subgroup generated by a squared. It's all powers of a squared. That's the kernel. And the image of f is just the identity and a to the 10th. Which the 10th powers are just a to the 0 or the identity and a to the 10th. Any questions about that? So this is the kernel. This is the subgroup generated by a to the 10th. Let's look at another example of the same thing. It's the same problem, part B. So my group gamma is cyclic group of order 20, generated by an element A. And we define the function f from the group to itself by f of x is x to the 5th. So f of an element a to the k, which is a to the k to the 5th, or a to the 5k, this is equal to e if and only if 20 divides 5k, or divide by 4 divides k. So the kernel of f is just all powers a to the 4k. And these distinct powers are, it's a to the 0, e, a to the 4th, a to the 8th, a to the 12th, a to the 16th. This is the cyclic subgroup generated by a to the 4th. In part C, we have f of x equals x to the 8th. So f of a to the k is a to the k to the 8th, or a to the 8k. And that's equal to the identity if and only if 20 divides 8k, which is the same if I divide by 4. 5 divides 2k. So 5 divides 2k, which means 5 has to divide k. So the kernel of this function f is again the subgroup generated by a to the 5th. Right. Any questions about anything? Okay. I think I'm going to stop right now. I'm going to be listing some office hours for the rest of the week and the weekend. But there's plenty of time to go over the rest of these questions in class too. Any questions before we end for the morning? Okay. See you next class. Bye all.
Thank you.